Okay, let's take a look at a difficult but kind of fun problem in astrodynamics or orbits, really. It was inspired by this non sequitur cartoon we'll take a closer look at in a little bit. I collected this and have always wanted to do something with it. Pretty much, if it takes one lifetime to fall, the problem is how high is a diving board? Now, they're landing on Earth, so we're just going to assume it's Earth's gravity that matters. We'll see that's not that great an assumption, but we can do it if we want. If you want to get your copy of your own cartoon, you can find it on the Non Sequitur website. So first, let's take a look at the cartoon. And so as the baby jumps off the diving board, goes through adolescence, early adulthood, retirement, and then splash. Life, it's not the size of the splash, but the joy you find along the way, because obviously after the splash, you're not around any longer to worry about it. And so how long did that take? Well, let's assume it's 80 years. I just picked that. You could look up some new average lifespan or pick something different if you want. You could assign this to students and give them a different time, and the answers will come out different. Now, there are different ways of doing this. This was a problem on my midterm back as an undergraduate in aerospace engineering, and it was very difficult. And then the professor, after we took the test, showed us an easier way that some students had hit upon. And it's imagining that that you're in an orbit as you're falling, and orbits are elliptical in shape, and it's so stretched out that it appears to be a line. And we know that the semi-major axis is kind of the average distance from the thing you're orbiting, which would be the center of the Earth here. And so that whole distance would be twice what's called the semi-major axis. Now, the time to fall then would be half the time it would take to go around once. Obviously, you're not going to go around once because the orbit intersects the surface of the Earth, but we can assume that. Now, this isn't to scale. As we'll find out, it's way out of scale. We don't know that yet, but Earth's radius is definitely negligible in this problem. Now, you could go and derive the equation for orbital period, but I'm going to assume that we know that or have derived it before. So the period is 2 pi square root of the semi-major axis cubed over big G, which is the universal gravitational constant, and m would be the mass of the thing you're orbiting, in this case, the Earth. And so we don't need to know the mass of the person. It cancels out if you derive it. And so then you could solve that for the semi-major axis, which is what we want. What is that distance? We got some really big numbers here, the mass of the Earth. We got a really small number, big G. And the period is twice going around, so I have a 2 times 80 here. Otherwise, you have to be careful with how you handle that. And then I convert that to seconds. So we have a big number in seconds, and that's squared. And so if you put that into a calculator, you get 1.7 times 10 to the 11th meters. And that's 78,914,000 miles. And so that is a huge distance. We'll put that in perspective in a little bit. And again, we're assuming Earth's gravity is the only factor. Now, if you want to try and solve this, including what would be the main contribution, the sun, there's a website you can go to that does this problem, finding out how much time it would take to fall into the sun. So in this case, they give you the distance, they solve for the time, and they do it with a more rigorous method that would conceivably let you figure this out if it'd really be the sun's gravity that would matter. And so what is 78,914,000 miles in the scale of the solar system? Well, sometimes we use a unit called AUs. And so 1 AU is the average distance of the Earth to the sun. And so I got this scale drawing of the orbits of the planets, and 0.85 AU is about that distance. And so you'd be falling starting outside of Mars's orbit. It's a little bit outside the furthest distance here Mars gets from the sun, and that's a huge distance. But notice the sun is here, so the sun's going to be pulling on you as well. And in fact, that would be the main contribution right up until you got kind of close to the Earth. So this would be a lot more difficult if you want to try and do it that way. Go back to that website at the bottom of the last slide and figure it out, and then you can make your own video showing us how you did it. So a lot of potential with this one with your students. You can pick different planets, you can pick different time periods, you can give them the distance and ask for the time, and so on.